beneath my feet, knowing I'm here to meet. Ocean's edge, it calls my name. Purpose in this life's game. Horizons line so clear, God's love brings me near. Flat earth made by him, my journey long yet thin. Purpose found in every day, guided by his gentle sway. Mountains to
Yay! Kate just arrived. Glad you could make it. How's it going?
Yeah, I'm fine, thanks. Yeah, how are you? Thanks so much for inviting me on. First of all, very privileged to
Anytime.
have you to have me on your channel.
Anytime. I appreciated the discussion you had with Solve, and I was like, yeah, no, that's how it's supposed to be done.
Absolutely. It was fantastic. It's the first time I've ever seen a discussion like that, where Globa and Flat Earth come together and there was no arguments, no bitching, nothing like that. It was fantastic. So much so that when after you had done it, Soft came over here, I put the link in, I went straight on and covered it straight away, reviewed it straight away, same night. It was fantastic. Excellent, bro. Loved it.
Okay, yeah. So, well, it's good to see you. Thank you for coming. I appreciate everybody in the YouTube land as well. Please hit the likes, share the show. PJ is going to be on mute the whole time, so don't worry. We were just having discussion because we weren't sure when you're coming on. But yeah, it's good to see you, man. And you can present what you need.
Okay, thank you very much. Yeah, I just wanted to start by saying, just a bit about me. I don't have a YouTube channel of my own yet, and I wouldn't describe myself as an anti-flat earther or anything like that. I do think flat earthers are wrong, but I don't think they're stupid, and nor do I think that they are anti-scientific. In fact, most of them that I come across use science to try and debunk the globe Earth model. And I also believe in attacking the theory rather than the person. So you'll never find me insulting a flat earther, although I may robustly argue a particular point that gets raised. But everyone's in here for the truth, right? So I also wanted to say that I understand the skepticism that some people have for the government and the mainstream and what they are told. And also that the starting point for everybody, before you're told about the globe Earth model, the starting point is, well, my eyes tell me that I live on a flat plane, and you have to be told that your eyes and your senses aren't necessarily the full and complete picture. And you find this out not just on the stellar stage or the celestial stage, but you see this on the micro and nano stage as well. So you get told that things are made of molecules, and then you get told that things are made of atoms, and then you get told that, well, even the atom is not the smallest thing. There's subparticles, there's protons, there's electrons, there's neutrons, and then even that's not the smallest level. I think the next level down is these quarks. They call them quarks, and then even quarks now they're suggesting you've got string theory. Perhaps the quarks are made of these tiny little strings vibrating and so forth. And then when you drill down to that level, you can't actually prove string theory. It's a theory. It's just way too small. Nothing that we've got could probe to that level. So there is, and what I said on Sob's channel is that the flat earthers are right in the sense that the Earth is almost flat, because on the globe Earth model, the sheer size of the Earth, it's so large that on our scales, it is flat to all extent and purposes. Nobody ever thinks that they're going over a curve when they commute to wherever they're going to, or from one town to another. It's just that they're told this, and obviously there are photographs and other things. So where I'm coming from is that a lot of the things that I'm going to raise, they're not things that are new. They're things that people have argued over before, and probably each one on their own wouldn't be conclusive, but it's just that my approach is that, taken as a whole, it's more plausible on a globe Earth, and it's more difficult on a flat Earth. And a lot of these points that get raised by people arguing in favor of the globe Earth, it's not that they don't work at all on a flat Earth. Some of them do, or some of them do with a little bit of sort of explanation and further theory. but it's a lot more plausible and more difficult on a flat Earth. It's more plausible on a globe Earth. And so just for me, taking that as a whole, it's just overwhelming that it's more likely to be a globe than to be a flat Earth or a flat plane. And our senses, the other thing I wanted to say, our senses, they've evolved for the purposes of survival of the species. They haven't evolved to inform you scientifically of the complete theory of everything. So you can't see atoms, you can't see molecules, you can't go into space and see the Earth from space because the atmosphere is uninhabitable up there. And so you have to question your set. You can't rely purely on your senses. That's why you have people that have done experiments, and that's why you get taught things in class, because other people have done things and you don't have to go away and prove each thing that's been done. So that's my sort of introduction to things. And then now, if that's okay, I'll launch into the individual points. Which
100%.
Yeah, you'll have heard these before, I'm sure, Flatzoid. So I'll start with the obvious one, which is just that the consensus is that we live on a globe. That's what the experiments have supported. And astronomers and physicists and scientists have all said that it's a globe Earth. There are some people who are in a position to know that it's flat, if it is flat. And the level of conspiracy theory that would be necessary to maintain the globe Earth fiction is just simply implausible in my view. People, in my view, things leak. Something would leak somewhere if this was a giant conspiracy theory. The other argument I wanted to make is just gravity and shape. The scientific explanation for why the Earth is a sphere is that when you have an amount of mass over a certain volume and mass and density, it will pull in all directions equally towards the center to form the spherical shape. And that's why the other planets have a similar shape, or the other celestial objects, so stars. You can see this with the telescope. You can see the moon with the naked eye. That they're all the same shape. There are some celestial objects that are not spherical and they're more of a rock shape. And if you look, for example, at the moons of Mars, I think they're called Deimos and Phobos. Very small objects. They're more rock. I mean, they're not flat, but they're quite rocky. And that's because they just simply don't have enough mass to pull in all directions. You look at some planets or bodies like the moon, they've got no atmosphere. Mercury's got no atmosphere because they're small. But where you look at the larger planets like Jupiter, I mean, Jupiter's pretty much all atmosphere. Uranus has got a large atmosphere, Neptune, the Earth, obviously, Venus has got a very large atmosphere. The objects that are over a certain size have gravity strong enough to keep an atmosphere. Some don't keep an atmosphere, even though they might be larger than the Earth or similar size. But that's more to do with the fact that they don't have the magnetic field that the Earth has, which repels the solar wind. The solar wind is a stream of charged particles, and being charged particles, they are deflected by the magnetic field. They tend to strip off gases and molecules from the atmosphere. So, yeah, the other point flowing from that is that if Earth were flat, we would observe something slightly different in that the gravity wouldn't be so uniform. There would be different parts with different levels of gravity. So that makes that a little bit more difficult without an explanation.
Yeah, you must just say if you want me to.
Sorry, go on.
You must just say if you want me to interject or if you want to make more points or whatever. But
no, I was going to say jump in if there's a particular point. That
okay.
Jump in
yeah, let me start off with the thing is with the gravity. It's just actually an assumption. I would agree. Everybody does observe things falling. Okay, and the assumption is that it's gravity that is the cause for that mass attracting mass, which causes ground. But that is based on the assumption that the Earth is a large lump of mass and the object has to be attracted to it, and that's what gives its direction. The thing that you just said about the gravity, that it would be different on all at different locations. Actually, there is differences in locations, even measured difference even on your globe. It's not much, but it's based because the belief is it's an oblate spheroid. The only thing is, you're trying to bring in gravity onto a flat Earth, and that's why it's not compatible, because gravity is only made specific for the spheroid. It's not made for the flat Earth. I don't know if you heard. I think Sov spoke to you about relative density disequilibrium.
Yep.
So it's practically the best I would take it is if you heard Eric Verlinde. He's a Dutch theoretical physicist. His whole take on gravity is entropic. So it's based on the entropic laws, natural laws. And how we look at relative density disequilibrium, it's explained based on that with a mixture of general relativity, because it's just simply the object is displacing the medium around it. And if the medium can't support it, it has to go back to seek its equilibrium. So if I can explain in a very simple manner, if I take this little spirit level here and I pick it up, I am actually inducing energy to pick this spirit level up. You would agree with that? So
Yeah.
my hand is able to support this, and it has now potential energy. Now, according to the globe, that would be based on the gravitational constant because of that energy. But I'm just saying the potential energy is just based on the distance to its next equilibrium. So if I had to put my hand here, it would give a different potential in kinetic here than where my hand is lower, because the distance has increased. So it's not gravity based, it's just simply the displacement ratios which gives its movement.
Thank you. Yeah, the only thing I would say about that is that how does it remember which direction it got pulled in to know which way is down without gravity?
That's saying. That's why what I was trying to explain is it's very subtle. There is no remembering. It's not sentient. So it took energy to pick it up. Just like a rock or anything, it took energy to pick it up. So because I had to pick it up and I had to use energy, it would be logically deduced that it would take more energy to make it go further up. So because I had to pick it up and I had to add energy to pick it up, the logical deduction is to use that energy, it has to go down. So it's not going to carry on going up, because why not up? Because it will take more energy to go up. So it's a naturally based law, just like entropy.
Yeah, but then if I've got this right, if you've used work to counter gravity by lifting it up, then it must be gravity that's then pulling it down, because you've got a force that's pulling it down that you're working against by pulling it up. So
Not actually.
What do you say is the force that's actually pulling it back down again?
Not actually. Even on your gravity model, it's not a force, because the whole paradigm in the globe at the moment is Einsteinian gravity, which is general relativity. So it's not a force at all. It's only an apparent fictitious force. Just like what I was saying, it was a mixture of that. This object is displacing the air around it. It can't support it. So it's warping the medium, and it has to have that acceleration because it has an unbalanced force.
Yeah.
So
I've just seen someone in the comment make a point, which is, well, when you move it sideways, why doesn't it come back to the middle? It only comes back, it only regulates up, down. It doesn't regulate.
Yeah, that's what I say. The whole...
Here's what I found.
Sorry, that's my watch.
No stress. The whole relative direction is based on natural law, just like entropy, where it's always hot to cold, it's always high to low. So it's always energy to low. Oh, sorry. You understand? So it's the natural tendency for things to go, because the medium has to support it. And if the medium can't support it, it can only go down. You can't expect it to go sideways, because that's not how support works. It's like a foundation of a house. You don't stick a foundation on the side of a house. The foundation is on the bottom of the house.
Right. So what about the vacuum tube then? So when you suck out the air, things still fall down in the same
Yeah,
way?
that's why I love when the people bring up the vacuum chambers, because the independent variable, which is your presumed cause for an effect, is the medium to object ratio. So in a vacuum chamber, when you remove the medium, the independent variable was the medium. You're not manipulating gravity. You're giving now less support for that object. That's why a helium balloon will sink in a, or fall in a vacuum chamber, because there is no air to be able to
Support it
support.
going up. Yeah. It's only going
Yeah.
up. It's not because it doesn't have a weight. It's because it's lighter than its surrounding material.
Yeah. So if the air's released, you've vacuumed the air out, there is no medium to support it. Therefore, it has to go down. And the interesting thing about in a vacuum, if you have to put something on a scale and you vacuumed that air out, does it get heavier or does it get lighter, the object?
Sorry, so can you repeat that?
If you put a object on a scale
Yeah.
and you stick in a vacuum,
Hmm.
when you release the air in the vacuum, does the object get heavier or lighter?
If it's in a vacuum, I don't, and it's resting on the scale, I don't see that the air would make any difference to the weight.
It actually does. The object actually gets heavier.
Well, it depends what it is. I suppose if it's a helium balloon, then it would be lighter on the scale. But if it was in air, because it would have a force pushing upwards on it. But if it was in a vacuum, it wouldn't. But what are you talking about? A helium balloon or
Just an object. I don't know if you've seen Action Lab. He's actually done a demonstration where he puts a little figurine on a scale in a vacuum, and it weighs a certain amount. As soon as he evacuates the air, that figurine gets heavier. So that's just what I'm saying. The independent variable is the medium to object ratio, because gravity would be if it's supposed to be gravity, it's not supposed to change weight.
Yeah, no, I would agree with that, but I'm not aware of that experiment. That's
I've actually shown it quite a few times. If you want, I can go and look for it, and we can see through it if you want to.
Yeah, you want to do that now, or shall I carry on?
Yeah. Let me quickly see if I can get it for you. You can carry on talking about it, something else while I'm doing it. It's fine.
Yeah, fine. Okay, yeah. So I think I've covered the gravity point. So obviously the next point is evidence and photographs. So there are photographs from space, and various space agencies, not just NASA, show this. And there's the International Space Station. And I'm not aware of too many videos or photos taken of the flat Earth that show a flat Earth.
The photos, well, it's a bit difficult, just like you said in the beginning, to have your scale, you can put it that way. To have the scale, Earth is very big, so you're not going to have to be able to see a whole flat Earth as it is. But we are able to observe flat Earth when we look out in observations like the horizon and things like that. You'd agree with that? So if we're looking out at a boat on the horizon, for instance, we see that horizon is consistent with not a curve, or sometimes you have optical effects that give it apparent curve. Now, the difference between the globe and flat is the globe claims that horizon is a physical thing, physical blockage, where we claim no, it's just optically that way, and that's why we do a lot of demonstrations on small scale on flat surfaces to show this. So we can explain it using diffraction, refraction, and limited angles and things like that, where the globe is just simply, it has to be physical curve.
Yeah, I think with the horizon, there are explanations on both sides of the argument, aren't there? The globe, the globe theories would argue that the horizon, the observations that we have at the horizon, support the globe Earth model because of the fact that objects tend to disappear bottom first, which is exactly what you'd expect to see if what you were observing was the falling away of the horizon in terms of the curve. So it's falling away from your eye line. But I know that there are alternative explanations offered by the flat Earth community about that, and I suppose people just have to make their mind up which is the more believable. I believe the flat Earth supporters say that if you zoom in, you can bring it back into view when the bottom's gone out of the horizon. And I've also seen one argument, which is that oh well, you don't see the bottom because there's waves and the water's not even and all that sort of thing, and wind.
Yeah, because I mean, obviously, when you're looking out on the horizon on the ocean's got, it's not water at rest. So there's waves, there's bulges, there's tides. You got a lot of things to contend with, even temperature variations. I mean, the temperature changes with distance as well. So it's not to say the temperature 5 kilometers down the observation is going to be the same as a kilometer in front of you. So you have temperature fluctuations throughout. When it comes to this observation, I don't know if you've ever heard of the word of diffraction before.
I've heard of diffraction, yes.
Yeah, so it's just simply when you, because obviously you've heard of the Aries disk, where in simple terms, if you got two resolvable patterns of light and they get too close to each other, the largest resolvable object is going to be resolved. So this is the argument: is the ocean is the largest resolvable object closer to you. So because the bottom of that ship, because it's going away, the angular size is getting smaller. It's getting less resolved bottom of the boat. Therefore, the resolved object is the ocean. So that's why a lot of the times they are able to zoom in, and then at the bottom of the ship comes back into view. But there are also points where you can zoom in and it doesn't come back into view. And that's why we say a lot of the time, well, it could be in a swell. It could just be based on foreshortening, because the wave would be blocking your view based on limited angles. Just like my thumb is not as big as my head, but if I move it close enough, you see it's foreshortening. It's covering my face.
Yeah.
So it's all just optically observed. That, in other words.
Yeah, and funny enough, horizon and curvature was going to be my next point, but you've now stolen it, so I'll have to skip through.
Sorry.
That's okay.
I've got that video for you if you want to watch it.
Yeah, why not? This would be a good time. Put it on.
Yeah, it's quickly. I enjoy Action Labs videos, by the way, even though it's a Globey, but I think it's really awesome stuff.
So this video is actually in support of the globe, is it?
Yeah, he was just trying to show you the differences, what happens in a vacuum chamber.
Right.
I'm not going to put the sound on, but you can see the weight in the corner there.
Yeah.
19808, and he's going to put it on now. He's going to vacuum it, and you're going to see it's going to get heavier. 19810, 1981. You see, it's getting heavier.
Well, it looks like it's going down. Oh, sorry. Yeah, on the dial it's going down. Is that? Sorry, the dial's the pressure.
Yeah, the pressure gauge is going down because he's releasing the gas.
Oh, I'm sorry, I was looking at the wrong thing. Yeah, so 192. That's the weight going
up.
Going up, right?
Yeah. So as you see, it's 19833, 19837, 19840. So it's going up.
Yeah, I would only be a bit skeptical about that because I don't know whether is the vacuum affecting the equipment, because the equipment would be designed to work in air, not in a vacuum.
Yeah.
Is it affecting the electronics in some way? Is the only thing I would be thinking about.
Yeah, well, you people can argue that because of the load cell, but I've also had people arguing to say, well, the air is not able to give it buoyancy now because the air is taken out. You understand? So that's why. Yeah. But the argument is the gas is pulled down by gravity, which pushes down on the object, and that's why it gives it, why it's supposed to be heavy. But now it shows gas is not just pulling down.
Yeah, actually, that would be the case, wouldn't it? So if it's low pressure inside, then you haven't got the weight of the air pushing down on the object. I would have thought that difference would be minuscule, but I'm not sure how accurate that weight measure is. If it's accurate enough, it could be measuring the difference in the pressure on the on the figurine. But I mean, it doesn't seem to prove anything one way or the other. I don't think it doesn't prove either case, because each side can argue that it fits their model.
Yeah, exactly. But my argument is, I don't think this shows gravity, because it's showing the case for relative density disequilibrium, because it's changing the ratio between the medium and the object itself. Because I don't know if you've watched me ever debate when it comes to gravity. I usually ask them, why is the independent variable never gravity?
Well, because it's constant.
But you see, because gravity can't be manipulated, how can it be scientific?
Well, yeah, but it can't be manipulated on Earth because it's a constant. I mean, you're right. You were right to say at the beginning that there are some fluctuations in gravity, but they're to do with altitude. So if the further you are from the Earth, the weaker the gravity. Only by a minuscule amount on these scales. Obviously, if you were like hundreds of miles away from the Earth, then there would be a significant difference, but not here. But I suppose it's measurable that, on the top of the Mount Everest, gravity would be very slightly less strong than on the surface.
Well, that's an interesting thing, though, because if you're claiming like mass is attracting mass, would it not be, for instance, Mount Everest, because it's part of Earth's mass?
Yeah.
If the air would be clumped together to Mount Everest. So let's say this is Mount Everest and you just got the air. You'll still have 14.7, yeah, but it's supposed to be, still being attracted towards Mount Everest, almost like, I don't know if you've seen ferrofluid before.
I haven't seen that, no.
It's a magnetic kind of fluid, so it's magnetically attracted. Imagine like Venom. It's like climbing over his hand.
Yeah, but
think of it like that. Why don't we see gas being attracted to Mount Everest in that way then?
Yeah, well, we wouldn't, because the gravitational attraction between Mount Everest and the air would be minuscule, immeasurable, because gravity is only strong when you're dealing with large numbers, so large masses like the Earth, for example, or the Moon or another planet. But even a large mass of air, they wouldn't have enough mass to attract. I don't know if you know this, but if you jump up and land, because of Newton's third law, every force has an equal and opposite reaction force. The Earth actually very slightly moves as well. Because it has to be the same force. So you land on the Earth with the same force that the Earth lands on you, and the Earth actually does move towards you by a very tiny amount. But we notice you moving when you fall, and not the Earth moving up, because the Earth is so much bigger that same force applied to an object that large doesn't really move it, whereas your weight is a lot smaller than the Earth's weight, and that's why that moves. So we wouldn't expect to see air attracted to Mount Everest, because the forces are just too minuscule. We wouldn't be able to measure that. That's a really, really small force.
Because it's seen as a weak force. I mean, even the electromagnetic forces are stronger, but still, that's all just based still on assumption, though, because according to Einstein, when, for instance, you go skydiving, you're not actually falling. The Earth is actually rising to meet you, because you sitting at, let's say, when you're in terminal velocity, you sitting, let's say, at zero G. Okay, that's why when you got the vomit comet, the people look like they're floating. They're still falling, but they're not actually falling based on their reference. So they look like they're floating because they're sitting on 0G, because the forces are now balanced out. So according to the globe, to general relativity, the globe is rising up to meet them, because they're not actually falling.
Yeah, I think what you're referring to is the equivalence principle, which means that from your perspective, because Einstein was very interested in people's perspectives, from your perspective, it's equivalent to the Earth accelerating towards you. And I don't think you're one of them, but I think some flat earthers subscribe to this theory of, you know what I'm about to say, don't you? The Earth is accelerating upwards to give gravity. And that would actually work in theory, if that were true. It would give you the same forces and feel as gravity does.
But you see, what I'm saying is, when it comes to relative density, because we get this a lot, they say, if relative density, then why don't the mediums and everything mix in free fall? You know, like when you shake a bottle and it doesn't sort itself out while it's in free fall. Well, it's very simple. It's just the same physics as you have for your gravity, because it's at the balance forces are now zero, because it's all accelerating at the same rate towards the ground. It can't support it. It's not able to sort itself out because the vector is on the same direction. Where if you have that same bottle and you shake and you just stick it down on the table, it will sort itself out based on its densities, because all the different objects and everything have their own impulse, their own unbalanced force. They have different amounts of force attributed to them. So that's why I say how do I put this in words I can try and explain? When you see the bottle accelerating, everything inside it doesn't mix because it's all accelerating at the same rate. So therefore it cancels those forces out. While the gravity explains it exactly that, but gravity's still keeping it as a force. So the problem with gravity, though, because it isn't seen as a force, it can't have those attributes.
Yeah, there's a debate in the scientific community about whether gravity is a force at all, and some believe it isn't actually a force. That they believe it's to do with gravity distorting space-time, and that when something falls, objects are merely they're trying to move in a straight line, but they can't because space itself is curved, so they're moving according to the curve. I mean, I don't actually fully understand it myself, but that's what they say. Like Einstein said, gravity tells mass how to move, and mass tells space how to bend.
Yeah. Well, you can draw it. Oh, the pencil's not working. You can actually draw it as a linear function on a piece of paper. Okay,
Yeah.
Space and time, and then you can curl it up as a cone,
Yeah,
and that straight line will seem to curve,
exactly.
and that's how general relativity explains it.
Yeah, that's basically it. I mean, it's not that
Yeah.
well understood, and some people say it's not actually a force like the other force, because you've got these other forces, like electromagnetic force and the strong nuclear force keeping neutrons and protons together and all that sort of thing. But it's there's a debate. I mean, gravity isn't that well understood by the scientific community, but I think what globe people are saying is that, well, you don't need to necessarily understand how it works to know that it's there. And it's pulling down in a certain direction, and it's doing it because it's a large piece of mass. And it explains why you've got the seas go around a curve, as it were.
But you see, that's where I have the issue, though, because they've made the assumption that gravity is there. So they're saying because a thing falls, therefore it is gravity, and then everything else hinges off of that assumption. So
isn't that how scientific theories work? So you start with, you call it an assumption, but it's a scientific theory. You start with your theory, but your theory is absolutely worthless in the scientific community until you can prove that observation supports it. So you're right to say that that's how the scientific method works, is that you come up with your theory and you try and prove it with experiment, and you say, look, I've done this experiment, that experiment, it shows it. Somebody else might repeat it and they may actually disprove it. And the other thing to say is that with scientific theory, what you tend to find is that there's an explanation given, observation supports it. It's believed to be correct, but that doesn't mean it's the complete explanation. And there may be some further understanding later. It doesn't mean that the old explanation is completely wrong. It means that it's incomplete. So, for example, you've got Newtonian mechanics, which, the classic equations about force and distance and energy.
F equals ma.
Yeah, thank you. I couldn't put my finger. F equals ma. There are a few other ones as well. Those all work fine. And that's the classic Newtonian mechanics. But then you've got quantum theory comes along and says, well, it's actually not quite that on the small scales. That's not actually true. And then you've got on the global scales and intergalactic scales, it's also not true at certain speeds. So relativity predicts that if you're traveling at something like 90% of the speed of light, then you observe something slightly different.
Yeah.
Right. You get
Yeah,
time.
it's almost like the Doppler effect.
Yeah, exactly. But I think on this point, it's probably something that neither theory, each theory has their own explanation, and neither one can just sort of disprove the other one completely.
Yeah, you see, the thing is, when it comes to scientific theory, you first have to observe, and then the assumption you make is the cause for the effect. So when it comes to gravity, they haven't actually made any I can say scientific validation for the assumption. They just, for instance, see this object falling and say, well, I see this object falling, so therefore I assume it's gravity. You would agree with that? The point is, now you have to take that assumption and you have to prove you have to validate that assumption based on hypothesis and experiment. My issue is I haven't seen yet a scientific hypothesis and experiment trying to validate that. I have seen people try and take the Cavendish and use that as a scientific hypothesis and experiment for that, but it is a category error because there is no actual independent variable for the Cavendish, and the Cavendish is actually showing torsion based on torque twist. It's calculating the G constant based on an oscillation measured through torque twist. You can have this based on many physics just with no gravity involved. I mean, if you have a rod and you have a weight on it on either side, it is imparting force downwards. So it has to put tension on there. That doesn't literally mean gravity is pulling it down to give that torsion.
Yeah. There's one problem I want to put to you, which is that when you measure the acceleration caused by gravity of an object, it's 9.8 meters per second squared, constant.
Yeah.
But on your explanation, why would it be constant for all objects? Surely it would depend on the medium, and it would depend on what object you've got and all that sort of thing. Why is it so constant?
Well, that's the thing. It's actually an average. That constant is based on average. If you look at the Cavendish papers as well, all those measurements they give are oscillations of different time that they actually had to make the constant. So it's an average. And your constant actually works in a vacuum. That's why they need to take the objects and drop them in a vacuum to get that 9.8 meters per second squared. If you have to do that in an atmospheric environment, you've got friction to contend with everything. And that's what I said, still making my point that it's the object to medium ratios and the displacement that gives the value for that constant. Because even the shape determines how fast it would fall. It's like taking a piece of paper. If I drop it like this, it's going to take long to get to the ground. But if I crumple it up and I let it fall, it's going to fall much quicker. Same mass.
Yeah, but we can explain that by the fact that there's a larger surface area when it's in paper form.
Archimedes principle.
Because it's in air, it's not in a vacuum. You've got a force pushing upwards, slowing down the deceleration.
Yeah, and that's my point. It's based on Archimedes principle. So it's relative density disequilibrium, as we call it. Interesting thing, though, I don't know if you know, Archimedes principle came out about 1,900 years before Newton postulated gravity.
Yeah, but I don't think it's Archimedes principle because is it not just because you've got the force of gravity pulling the paper down and it's moving against air, and obviously air has got some resistance and that's pushing the piece of paper back up. Archimedes principle, isn't that about you get into a bath and the water moves up by the amount that you... It's
displacement. Archimedes principle just literally talks about displacement. It's like that's why a ship with 1,000 tons can float on water, because it displaces the pressure, it displaces the weight around it. But that's what the paper does. When it's falling, it's displacing based on surface area. That's why it falls slower. So it's aerodynamics. I'm trying to think of another way to try and explain it, but it's just simply the displacement ratio is based on its surface area, how much it displaces. That's why the speed is falling the way it does. So you can take a bowling ball and drop it out of a helicopter. If the wind is strong enough, it's going to take longer to fall, because obviously the path it'll take is longer because it's going to go left to right. Or if you have a bowling ball that has a one side flat surface, it's going to tumble whatever, because that pressure is pushing against the surface. So that's why I say the constant they have is only based in a vacuum, because it takes that resistance away, that friction.
Yeah. Okay. Well, so let's imagine that instead of a piece of paper, it's a metal sheet. Let's say it's a metal sheet 1 centimeter thick. Okay. And you put the metal sheet, because you accept metal's heavier than water. So you put the metal sheet, or more dense, I should say, rather than heavier. So you put the metal sheet on the surface of your bath, you fill up your bath, and it's going to sink. But it's not going to displace the same amount of water as it would if, instead of a flat sheet of metal, it was a ball or a cube. So Archimedes' principle would predict that they would displace exactly the same amount of water, because they've got the same volume, haven't they? It's just different shape.
Yeah. I think it also gets on how it's placed in the water. If you take that metal sheet and you stick it down calmly on the water, it's able to, the surface tension around it will also maybe hold it up. But if you have to just plonk it down, it can sink.
Yeah, it'll sink faster if it's in the shape of a cube than a flat piece of metal. That's for sure.
Yeah, that's why. Also, let's for instance put let's take those little children's bathtubs. It's a little plastic tub. Okay, on its own it can float in the water. As soon as you climb in, you're a bit too heavy for it, and it would sink. It can't displace the weight anymore, because now you're too heavy for that surface area to displace it.
Sure.
So that's why it sinks. But my point is the weight, because gravity, according to the globe, gravity is what gives weight. You'd agree with that?
Yeah, because weight's actually not a measure of mass. Weight is the force that an object exerts.
Yeah, it's a force that exerts on a scale.
You're weightless. You're weightless in zero gravity, but you're not massless.
Exactly. So that's why I said it's at the bottom line, it all hinges down to density, because everything has mass. Everything, has a substance per volume. So you always have mass, but you're still moving in a direction without having weight when you're in free fall. So therefore, I'm against saying gravity is pulling you down, when it's just simply you're not able to displace the medium, so therefore you're falling through it.
Okay. Well, anyway, shall I move on to the next point?
Yeah.
So I've got both of these under the same heading: time zones and seasons. Mm-hmm. So I know that there are some elaborate explanations for how you can have time zones and seasons on a flat Earth, but it's more easy to understand on the globe. So as you know, you've got the different latitudes on the globe, and the further up it is, then the less it's pointing directly at the sun. So it's not getting the rays. It's getting the rays obliquely rather than directly, and that explains why when you've got the extreme northern hemisphere and the extreme southern hemisphere have colder climates than at the equator, and with the axial tilt does explain the seasons very well, and it explains also why you've got the overhead sun at latitude, I think it's 23.5 or something. You've got the Tropic of Capricorn and the Tropic of Cancer, and the axial tilt is exactly that, to show that. So when it's summer for the northern hemisphere, then the Tropic of Cancer, if you're on the Tropic of Cancer on June the 21st or thereabouts, midday sun, or the zenith anyway, it might not be exactly midday, but the zenith will be directly overhead. Mm-hmm. That's beautifully explained on the globe Earth model, and there are explanations with the flat Earth model, which I'm sure you will share, but they seem more sort of elaborate. It sounds like you're trying to.
Well, you see, the thing is how it's just been observed for certain times and seasons throughout the years. I mean, I don't know if you've heard of the solar cycle before.
No, please explain.
Okay, well, the solar cycle just explains cycles that's been going on for like eclipses and stuff for centuries. It's
Right.
observed. It's the same with the seasons. Now, the model of the globe has just taken all observations and the times and seasons and placed it onto a sphere to make it that if you didn't have your 23.5 or 23.4, whatever actual tilt, it wouldn't work on your globe. You need that specific tilt. And
Yeah.
interesting fact, it equals 2,666, as people like to make fun of it because of that. It's minus 90. But it works exactly the same on a flat Earth. The only difference is it's flattened out. Where a globe, it's over a sphere and it's wrapping around the sphere. You can take that same thing, you can just flatten it out, and the same takes the same path.
Right. So how do you explain the time zones and the seasons on the flat Earth model?
Well, it's explained as the sun taking a circuit on the flat Earth model. So it's taking a circuit, and usually when it is, the sun changes in altitude. So you can look at it as
Well, what makes it change altitude?
plate.
What makes it change altitude on the flat Earth model?
the sun. Look at it as a. I'm not going to say orbit, but I'm going to say look at the plate. Now say this is the sun, and it's when it's spinning, it's doing this kind of wobbly thing. So when it's higher, it's winter, and when it's lower, it's summer. So it's when you spin something, but then it spins like that's the thing. So on the flat Earth, it explains it when the sun is closer to the surface, it's summer, but when it's further away from the surface, it's winter. So right now I'm in the southern hemisphere, it's summertime, so I would say it is tilted this way, closer to me.
So you're saying the sun is what tilts?
The sun follows a circuit. So where I am here, the sun is closer, and let's say where you guys in the UK, because it's winter time by you guys, the sun is a bit higher by you guys in the north. It's just a very rudimentary explanation. It's like closer to oven, hotter, further away from oven, colder. But that's just the way the flat Earth explains it.
Yeah. Do you say that the sun is that shape, a sort of flat sphere, a flat circle?
I don't know, because I do think it has sphericity to it because it's observed to have divergent rays. But I can't say it's a full sphere. I can say it's maybe a half sphere, but I don't know what the sun is, and I can't really make claims about it. But I do know the sun gives us light. There's a lot of things attributed to the sun. But based on what it is and really how high it is, I can't say. That would be me being dishonest if I say I did. You understand? So,
I'm just trying to understand it, because if it's the sun tilt and it's tilting towards, so that would mean I'm just trying to get my head around the relative sizes of this plate. So it'd have to be, the sun would have to be at such a certain distance where that would happen.
Yeah, because like I said, I think it moves in different. It's a relative position moving. So I don't think it's an actual position to say. I'd say it's more based on apparent positions. Even on your globe, actually, when you're looking at the sun, you're not actually looking at directly. You're looking at the refracted location of the sun. So when we observe the sun in the sky, it's not at its actual location. You understand?
How far away do you say it is from the Earth's surface?
I wouldn't be able to say. People try and use trigonometry to try and work it out, and then they come at like between 3,000 and 5,000 miles. But that's just them with trigonometry and ignoring optical things like refraction and things as well. So I've actually had this the same thing with McToon before, where I did trigonometry for the sun, and it shows the sun at different locations, different altitudes, just based on location alone. So it changes the elevation of the sun. But the only thing we can really do with the sun is observe it optically, which perspective comes into play.
It is observed to be slightly larger in January and slightly smaller in July. Do you accept that? And how would you explain that?
Yes.
I mean, you do accept that?
Yes, yeah, I do, because it's usually like a half a degree or something difference. But like I said, I think that difference is because it's closer to the Earth in summertime and further away from the Earth in wintertime.
Yeah, but it depends which hemisphere you're in, because I think January would be summer in the southern hemisphere.
Yeah, that's what I say. That's right.
You get the best of both worlds, don't you? Because you get the sun closer to
Where I am now, I'm more in the bush, so I'm on the top of the northern parts of South Africa, so I'm closer to the equator. So it's quite hot here. Let's put it that way. It's very hot here and stuff, but it also can get cold. So where it is going on, I'm close to the Tropic of Capricorn, and in the summertime it would be like I was showing with the plate tilted. The sun would be following this arc. When it gets to you guys, it's higher. When it gets to me, it's lower in winter. And as soon as it gets to summer with you, it's making this, and then now it's lower to you guys and high at me winter. And I think that's just me trying to explain why it is. Yeah,
it also does that. Does it over the flat?
Yeah, it still takes its circuit, but it's taking a wobble, and that's why we see the analema. You know that figure 8?
Yeah, I understand. Yeah, I've seen that figure 8 over the course of the year.
Yeah. So that's what I said. It's the same explaining as a globe. The only difference is with the globe, it takes the wobble. So the globe has the axis tilted wobble, where the flat Earth has the sun having the wobble and its axis.
Yeah. There's going to have to be a wobble on both models to explain it. Yeah.
So it's the same on both.
Yeah. Okay. My next point was circumnavigation.
Mm-hmm.
So sailors and aviators have traveled around the world continuously using compasses and arrived back where they started. And even I think Magellan did it some time ago, circumnavigated the globe. And the other point related to that is that that certain flight paths have been taken which would only be possible on a globe Earth. So, for example, if somebody's flying from New Zealand and going the other direction, not the classic direction westwards, but going eastwards, they can arrive at a point that is on a flat Earth would be considered extreme west. And the last point I wanted to make on that is that if you take a straight line between London and New York on a flat Earth, like a map, that should be the shortest distance. And you can work out at a certain speed how long that flight should take. Actually, the flight takes less, and it doesn't go that way. It goes up, skirts the southern tip of Greenland, and then down south to New York. And that is the fastest route, or one of the fastest routes on a globe curved. So that's another argument. And the Great Circle routes the airlines use only make sense on a spherical Earth.
Well, I don't know if you've seen emergency landings by Banjo before. It's 27 emergency landings. He shows quite a few where they done emergency landings and things where it only makes sense on a flat Earth. So, for instance, a pregnant woman was going into labor and they had to do emergency landing, and I think they went through Alaska or something to get there, but on a globe Earth it's totally out of the way to get there, but a flat Earth it was a straight path. So I would agree that on some cases it shows a globe for paths, and some cases it shows a flat Earth for path. But also have to understand the map being used is the Gleason's map usually. It is distorted just as every other map is distorted. The distances are the same as every other distance. Because I've been trying to explain this to people. When they measure, for instance, distances, okay, it's not really shape dependent. It's just a measured distance. Your map, you can have that same map on a triangle, and the distances are incomparable to that same distance, because with the AE map, it's not based on distances. It's based on the Gleason's AE map is just based on the sun and the sun's position and time. It's not made for distance based. So, like when you have, for instance, I'm trying to get it into my head, I can explain it. Like when you have a Mercator map, the continents aren't laid out perfect. They have distortions. You'd agree. So like Greenland's different, and Africa's different sizes and all that, but the distances are correct. So it's the same as on the AE map. The map distortions are out of whack, but the distances are still the same. So when you're saying, okay, I just see this large body of water, therefore it can't work on a flat Earth. No, the distance is still the same. It's just the continents, everything are moved to support that certain map.
Yeah, I think I see what you're saying. So, but what you're saying is that the map that we use assumes a globe, and therefore it's actually distorted versus what a flat Earth would really be.
Yeah, it works in the grid system. So it works in your Cartesian system, which is latitude and longitude.
Yeah, because I think on the globe Earth model, the traditional map that we see, the 2D map, is distorted. I think the size of Greenland is shown as it's actually a lot bigger than it is shown on the map, but necessarily it has to be. And I'm sure we've all seen that one where Antarctica is just like a huge, it goes all the way across, doesn't it? Because on a globe Earth, that's what you would get if you converted it into 2D. You'd have to distort the extremities.
Yeah, that's the Mercator. That's the most widely used map. But like I say, it's all just based on the grid system. So you got a block based on that grid. It's for the latitude and longitude. That distance stays the same, even if it's distorted onto a map. That distance is still the same. So you can have that block distorted this long. You can have it distorted this short. That distance measurement between the two is the same because it's based on scale. So you can take that same grid and wrap it around this mug, and let's say we fly around a mug Earth, just because it follows that grid system. You understand?
Yeah. Okay. Well, I mean, neither of us can jump on a plane.
No, we're not. We're not cartographers or anything, so we can't really.
We can't. All right. So my next point is the lunar eclipse. I'm sure you're familiar with this point. That the lunar eclipse, which is when the Earth is between the sun and the moon, that shadow or that shape cast onto the moon is consistent with the globe Earth, with the spherical Earth. It's a circle, and with a flat Earth, we would expect a different shape. So I don't know what you say about that.
Well, okay. I first got to ask: Are you trying to think that the flat Earth is in space? Because we see this a lot, like Neil deGrasse Tyson or something saying, "Oh, you're supposed to see a flat pizza in space, so you'll see just a flat shape."
Well, I don't know. Because it's not my theory, so I don't know what is being said about it.
Yeah, I don't. Flat Earth doesn't claim we're in space, though. So that's the first thing the globes have to understand. I specifically ascribe to the Hebrew cosmology. As the Bible describes, so it would be we're encased in the waters, so we're not in space or something. So when it comes to the eclipses, I don't know if you've heard of the impossible eclipse before.
No.
Well, let me see if I can quickly get it. What happens is you have the sun and the moon at two different sides of the observation at the same time while it's eclipsing. And the shadow is a total 180 degrees opposite of what the Earth is showing. It's impossible. It's called the impossible eclipse because it's not possible on a globe.
And this has been observed?
Yes, they observe it quite a lot.
Yeah.
Let me see if I can quickly get it up. They call it the impossible eclipse. But there's a certain name for it. Not impossible eclipse. Because I think the argument they give for it is a very extreme refraction. I think this is a photo. Yes, open image, new tab. The impossible eclipse. Okay, let me see if I can quickly share. Is it showing?
Yeah.
Yes. Okay. So what happens is you can see the shadow takes a very certain type of arc.
Yeah.
But you can see it's coming from the top.
Yeah.
if the Earth is supposed to be the reason for the shadow, why is it coming from the top and not the bottom?
Well, I know that's what happens on a solar eclipse. You see the moon's shape; it tends to come from the top, doesn't it? And it comes across.
Yeah, but this is opposite. And this, I don't know if this video is showing it to right. Also, the issue with this is, for instance, there's the moon. Okay, I see the shadows from the top and not the bottom.
Yeah.
The Earth is supposed to be the reason for the shadow, but the shadow's inverted. And also, the sun is on the other side. So, in other words, if the moon is here, the sun is this side, and you are standing here watching the moon be eclipsed by the Earth that's not eclipsing it. You understand?
Yeah, I think I understand what you're trying to say. But people have got YouTube videos of it being completely consistent. They've got the opposite of what you're showing.
Yeah. There's definitely eclipses that show according to, like you guys would say, the Earth is blocking it. I can't
That's
fight
a good
against.
point that you've raised. I don't think I've seen an explanation for that. But why is always from the top? Because when it's a solar eclipse, it does tend to be from the top. And there might well be an explanation for it. I don't know what that explanation is. Why
Yeah, the only argument I've ever got is refraction.
Yeah.
Very, very large amounts of refraction. But I mean, why is it inverting it? It's not supposed to invert it.
What do you mean inverted? I didn't quite understand that.
How do I take it? So, in other words, like I say, because the Earth is supposed to be blocking it from the bottom, so the shadow should be bottom,
I see what you mean. So
and the shadow's coming from the top.
It's coming
So
from
the Earth is not causing the shadow.
But why couldn't the Earth? Why couldn't it be below? If the Earth was here relative to the, so if you've got the sun here, and the Earth here, and the moon here, then wouldn't that explain why it was at the top?
No, because if it's this way and you were standing here, the shadow of the Earth should be at the bottom. Understand?
Yeah.
Otherwise, the Earth should be like this, and you can't see through the Earth to see the moon. And you see the sun and the moon both in the sky at the same time above the horizon. That's why it's impossible.
Yeah, that I agree. Sounds impossible if they're both, because if the Earth is blocking the light from the sun, then would you be able to see both? Well, actually, you might be able to see both. It depends, doesn't it? Because if the Earth is in the way, then surely when you look that way, you can see one, and when you look that way, you can see the other. So why wouldn't you see both?
Yeah, because according to the globe model, the Earth is supposed to be blocking the sunlight. So the Earth's blocking the sun to give the shadow on the moon, and it should be coming from the position of the sun. But because the sun and the moon are both above the horizon, that means the Earth is not blocking anything, and the shadow is coming from the top down, not bottom up.
Yeah,
but I think you're going to have to look into this further, because, like you say, you haven't actually looked at it.
I haven't looked at it, but I'm not convinced that is necessarily right. That you wouldn't be able to see both, because, for example, in a solar eclipse, there's only very rare times in a solar eclipse where it's the moon blocking the sun. Most of the time, you've got the three objects are in the sky, and you can have one here, and one in the middle, and they don't block each other. It's only a very rare. It has to be an exact fit where it blocks it.
Yeah.
So I'm not sure about whether when you just seeing two in the sky at the same time means that one isn't blocking the other one.
Yeah. Well, what I'm saying is, it's just, I'm going to try and explain it now. Okay. Let's say that the sun's light is going now. Okay. So it's lighting up all this path. Now we're supposed to see shadow. I'm going to make it red now, because the Earth is blocking it there. You understand?
Yeah.
So in other words, this is supposed to be shadow.
Yeah.
That's not shadow showing on the impossible eclipse. The shadow showing on the top.
Doesn't it depend where you are? What about if you're in the southern hemisphere?
It's obviously location dependent because you have to see the sun and the moon at the same time in the sky. But you see the issue. If the shadow is supposed to be here, why is the shadow up and not in the bottom?
Yeah, I've just been looking up myself. So I think that you're right that you're not supposed to see. The moon is in Earth shadow, so it should be physically impossible to see both the sun and the moon simultaneously during a lunar eclipse. That is right. So if that's what's been observed, then that would be remarkable because it would disprove the lunar eclipse.
Yeah, but I think you should go and look at that a bit further because it's an interesting subject to look into.
Oh, definitely. Okay, so the southern hemisphere stars is another example, and the position of the North Star. So the constellations visible in the southern hemisphere differ from those in the northern hemisphere, and that only makes sense on the globe. Stars appear to rotate around the North Star in the northern hemisphere and the Southern Cross in the southern hemisphere, and also the fact that you see the moon inverted in the southern hemisphere compared to the northern hemisphere.
Yeah, there's definitely different star systems. Because I'm in the southern hemisphere, as I put it, I see the Southern Cross, the Milky Way, and all that. You guys see like Polaris and Big Dipper and all that, which I don't. Everything has limitations to it. So obviously, it's not in my line of sight to be able to see it because I don't know if you've. I'm going to quickly show you something, a little graph I made a while back. Yeah, I'm busy working on my own relative density disequilibrium equation at the moment as well. Really want to get that out soon. But anyway, this is based on Polaris. Okay, if you're standing 90 degrees under Polaris.
Right.
Now, if you're walking further away, this would be 600 nautical miles. This is based on the 1 degree per 600 nautical miles drop. On a globe, you would be claiming that Polaris has dropped 10 degrees physically. But on a flat Earth, it's only apparently dropped 10 degrees. So it's keeping with perspective. So the further you go towards the equator, when you finally do get to the equator, you see it has dropped. So that Polaris has now, in your line of field, dropped to the equator, to the ground. So you've physically observed it going down, like perspective dictates. You'd agree with that?
Yeah.
So because it's that way, that's what a hemisphere is. Now, you can only see the northern stars take that path, just like I can only see the southern stars take that path. The further away I go from the point, the more drops due to how perspective you would see a light pole, for instance, in the distance look like it's coming towards the horizon because it's converging. That's practically all that this describes. So what this dome here is based on what I would say your limitation to view. So like a field of view kind of bubble, you can say, because you got a radius value of limitation that you're able to see. I think you'd agree with me that everything has limitations. Even visually, you are able to only see as far as you can. Light has limitations as well. If I like to explain it this way, you can take two people that have they're smoking, so they've got a cigarette butt, and there's two mountains 10 kilometers apart. They both go to the top of the mountains at night. They light the cigarettes. Would you expect them to see each other's cigarette butts 10 kilometers away?
No.
Yeah, and it still wouldn't be Earth curve blocking them. It's just the light isn't able to reach the other observer.
How do you explain the moon being inverted on this? If it's just it's a flat plane and it's just a different distance.
Moon inverted? Oh, because you say it looks that.
Yeah.
If you actually observe the moon throughout the year, you would see it actually has different rotations. Sometimes it looks like it's a bunny by me, And in other times of the year, it looks like it's upside down bunny. It actually rotates. You actually get people who have taken observations where they see it rotate clockwise, the moon. So they actually see it rotating clockwise.
I don't think I've seen that.
That's quite interesting as well.
That would be interesting to see. And by the way, I was just looking up on the point about the eclipses. So it is possible to see both. You're not supposed to, but it's to do with the refraction. So the atmosphere.
See, I told you.
Yeah.
Told you refraction's the argument. But how does refraction invert it?
It's funny, isn't it? Because refraction's used by both sides, depending to get them out of a.
Yeah, exactly.
Sometimes refraction works for the flat earthers, and sometimes it doesn't, and vice versa.
Yeah.
But yeah, I mean, it does explain. And you're right. You're not supposed to on a pure theoretical basis, but then sometimes you see. It's also used for the old Chicago. I don't know if you've seen the meme with the Chicago
skyline. Yeah,
the Chicago skyline. But you can sometimes, you don't see it all the time, but when you do see it, it can be due to the refraction going over.
Well, you see, that's where we differ. We say due to refraction, you don't see it. So when it's a clear day, you do see it. Where you guys say it's opposite, it's due to refraction that you see it when it's not a clear day.
But you don't always get the refraction. You only get it if you've got a certain weather pattern to allow. Yeah. That's what
I agree. That's what I said. It makes it a clear day, and therefore it's taken some of the refractive away for you to be able to see it. So where you guys claim the refraction takes away the Earth curve, we claim the refraction gives the Earth curve. I can show you. I want to actually show you. So, have you ever watched some Sky Freeze? Have you ever heard of Sky Free before?
No.
YouTube channel. I just want to quickly show you a demonstration quickly. Just want to quickly get it up. This channel does a lot of small scale demonstrations with refraction. Really, really awesome stuff. I want to see what's the right video. There's two of them actually. Let me first show this one. But I must say, I'm enjoying this chat, man. This is the kind of debates I like, because we can all actually understand what's going on. No one's talking over each other and fighting and going haywire.
Yeah, and the points being raised are interesting ones and good ones.
But I'm enjoying this. I think we should do it again sometime. It would be great. Okay, you see they're taking all the different temperatures and everything. What happens is they got a buttons. Let's see if I can get where it shows the buttons. On the ground. There we go. You see?
Yeah.
These all buttons. So what happens is the camera is now low on the ground, and they're going to open the door now and let the cold air in. So it's going to cause refraction now. And while they're doing this, the refraction is going to cause these buttons now to be lowered into the horizon. You see there?
Yeah.
So the refraction is causing what you would call Earth curve.
So you're saying that the refraction should make it go even further below the horizon, not bring it up.
Yeah. What I'm saying is the refraction causes the optical obstruction, where the globe claims the refraction takes that optical obstruction or that physical obstruction away and just makes it optical to be able to see it. So, in other words, the globe claims that those buttons should be seen due to refraction over a curve, where we're saying no, it's the refraction that causes the things not to be seen. So when it comes to like the Chicago skyline, the argument I would be making is, yeah, it's most of the time it's the conditions are so refracted you can't see it. So when the conditions are clear enough, that's why you see it, because it is literally there.
Oh, okay, yeah. So you're saying when you can't see it, it's because it's refracting. So you're actually using the same argument, but in your favor.
It's in reverse, yeah.
As it were, yeah. All right, fair enough.
and this is another one which is really cool, where they use a laser. Let's see where it gets to that. Is it this one? Yes. And the laser does a very interesting thing, because as soon as they introduce it, the laser also goes below that ground, but on the on this measuring thing, it goes up. You can see it's lifting up there while it's going below the horizon. So it's showing you the distortion of the light. So it's creating the effect of it going below the curve. That's all I want to show you. But I'm going to put these people's link for you as well, like if you want to go watch them sometime. They got a lot of observations.
Please do. So a similar point allied to this one is the Burj Khalifa. I'm sure you've seen this, where there's the tallest building. I think it might be the tallest building in the world, but it's in Dubai. And Dubai is blessed with having quite clear skies and very little cloud cover and rain. So you can go there and you can observe the sun setting across the horizon on the ground floor. You can get in one of the really speedy lifts, go to the top, again, and then watch it set again. And that is consistent with what you would expect on a spherical Earth.
And a flat Earth.
Yeah. So tell us why it also works on a flat Earth.
Okay. I think Mr. Sensible did this thing as well when he went to Dubai and he did this. It's just because you're opening your field of view. If you are going higher, you'd understand the reason you can see further is because you're opening that angle. So remember when I said earlier about diffraction? And the graph I showed you earlier now with Polaris dropping with distance. So if you had to raise higher, because I think you've done this probably before, you can take your camera and stick it as low as possible to the ground.
Yeah.
You're going to see your field of view is going to shrink, because you're going to see mostly more of the ground now. But as soon as you get up, that field of depth is pushing out further. So you're able to see further and further.
Yeah, so I'm just trying to envisage so if I'm on a flat Earth, the sun is a disk up there, so like 3,000 miles away or so, and it's going away from me, so it's going lower and lower and lower. It's gone past the horizon. So you're saying if I go up, then I can see on top of it, kind of thing. So it brings it back into view, basically.
I've actually got a demonstration I did in a spray booth before, with the paint cans and stuff. I'm going to quickly get that for you, where it shows this exact thing, where you're raised in altitude, you're able to see further on the flat Earth. Just have to quickly find it. I used to do so much videos. But how, anyway, did you get into the whole flat Earth discussion thing, though?
I think I've just been watching a few YouTube channels, probably similar to your ones, and I just sort of learnt about it. I'm not a scientist or anything. I've got A levels in physics and chemistry and so forth, and I actually went into law and left science, but I've always kept a keen interest in it, and I just find that the whole sort of debating side of it quite interesting.
It's amazing. Everybody,
it's
amazing. Everybody has their own way of getting into it.
Oh, absolutely, yeah. So I mean, I've just been looking a few things up about the Burj Khalifa and the difficulties for the flat Earth model. So, flat Earth, I think flat earthers argue the sun is just moving away, not setting. But if the Earth were flat and the sun was simply moving away, ascending to higher elevation wouldn't allow you to see the sun again. The angle of view would remain the same regardless of height. On a flat Earth, the horizon would be at eye level no matter your elevation. Observing a second sunset from the top of the Burj Khalifa contradicts this claim. You would dispute.
Is that WS? Are you reading that from WS site or something? Or McToon?
I've got it on a Google Gemini, so it's just come up with that.
Yeah. Well, you see, that's the thing. They're ignoring things. look, I'm going to show you here. Okay.
Yeah.
I got a torch here and it's on paint tin cans. So all I'm doing here is just simply showing as it moves away, it's going to drop to your perspective. See, that's the closest position,
Yeah.
furthest position, or anywhere. You can see it's behind the tin can now. Let's say that's like what you are. You're on the ground floor of the Burj Khalifa now. Okay. And the light has now gone that you can't see it over the horizon. So there's, for instance, a mountain in the way down there or whatever. It's blocking your field of view because of your angle. But look what happens as soon as I lift the camera up. Let me go back. Look what happens when I lift it up. See, I'm able to see it now.
Yeah, but isn't the difference that that's not, the light source isn't up and just moving further away. He's actually brought it down to the floor.
No, this is a demonstration I did. The light is exactly the same height from the closest position to furthest position. It's exactly the same height. It's on top of a paint tin can. I've just moved it further and further away.
All right. Okay.
So due to perspective, it's dropping to the convergence of level. Okay, of the relative eye level, and now this paint tin can in the front is now blocking it because it's foreshortening it. The angle is blocking it. Just like if you were in the bottom of the Burj Khalifa, there's things blocking your field of view due to the sun's apparent position dropping to the horizon.
Yeah.
So as soon as you're going to go up now in the Burj Khalifa, you're going to be able to overcome that angle that's limited and you'll be able to see the sun again.
Just see it again. So that light was at the same height all along, was it?
Same height the whole time.
Okay. Well, I have to accept that what you've done there does seem to show what you're saying. But obviously it's consistent on both models then.
Yeah, again, that's the issue with the whole globe flat earth thing. There's always answers on both sides. It comes up to which are you going to be honest with yourself and just choose, to me, I haven't really seen anything based on the globe more than just assumption and people taking it for what you've been taught. The whole thing that actually got me more into flat earth and understand it because I actually studied art. I went to major in art and things, and perspective is one of my passions that I always wanted to, and when I was down at the beach, I actually was able to understand and explain that based on optical things with perspective and things, and that's what actually got me into the flat earth. Because I also first heard of it and I thought, oh, this is nonsense, rubbish, whatever. And later on, it just, I don't know, it was like a light bulb in my head. And that's when I looked into it further. And today I'm a flat earther.
Yeah, it appealed to you. Yeah. Well, one thing I wanted to bring up, I'm not sure if it's something that you argue, but I have seen these arguments about water not sticking to a ball.
Yeah.
And also the arguments that the Earth is spinning. I've seen the one about the helicopter. How come the helicopter doesn't?
Coriolis.
Yeah.
Yeah, with the water not sticking to a ball, that's more of a joke kind of thing because obviously it's a straw man because the globe would claim that water won't stick to, because that ball is not a large mass as the Earth. It will still be anyway attracted to the large Earth mass. So it's a straw man anyway on physics. But the whole claim is, look, you can't see any water sticking to this ball, so how can you claim it sticks to the Earth? I understand that's just a straw man, but I see that more as a joke as anything. But when it comes to the Coriolis effect, I don't think we observe Coriolis effect. The issue that you guys have with Coriolis is what we call globiolis. You sit in a bit of a paradox because you need the Earth you need the atmosphere to be velcroed to the Earth to give that momentum to move. But at the same time, you can't have the velcroed air to observe Coriolis. Understand?
Yeah, well, the Coriolis is one of the arguments in support of the globe Earth because you've got it in the same direction, and it's because the atmosphere moves with the Earth, yes, but not necessarily exactly at the same speed as the land. And the Coriolis effect never crosses the equator because it weakens at that point. But it's
Yeah,
one of those ones where you can't say that on its own proves that the Earth is a globe. It's just another one of these factors. It is beautifully explained by the globe Earth model, and it seems a little bit more tricky to explain on a flat Earth model.
not actually. I've done another demonstration as well, where I was explaining tides and stuff in a fish tank. I don't know if you know about thermohelian currents.
No.
So it's just plainly based on thermodynamic tendencies, so hot to cold, and that. So that's what moves the conveyor belt of the sea thermodynamic currents. It's the same thing how storms and systems work. So because the Earth has topography, and we got Bernoulli's principle. So if you, for instance, have a mountain, the air is rushing past. As it's rushing past, it's speeding up. So it's creating a low pressure system. So it's moving it in that direction. We got air currents, and you've seen the air currents over Earth. On a flat Earth, it shows it more symmetrical, but on a globe, it kind of makes it go. All those eddy currents and stuff go in different directions and gyres and all that stuff.
But what makes it move always in the same direction and in opposite directions on depending on which side of the hemisphere you are?
It's the air currents. So because we've got air currents based on movements like storms and things, just like, I mean, the hurricanes and stuff, for instance, okay? The reason it would spin anti-clockwise and clockwise in different hemispheres is simply because the path it's taking through on the ocean. Remember, it starts as a cyclone on the ocean.
Yeah.
So it's the air is pushing it. So how it's formed is the hot air is rising and the cold air is taking its place. So it's causing a vortex. And because it's pushed in that direction, it can only spin that way. So that's why you don't get any hurricanes, you could say, on a specific when it gets to the equator. It can't happen because I'm trying to.
But what I'm struggling to understand is that how do the airflows know exactly where that boundary is between? Because I mean,
It's just the air current. It's just the air current moving through the equator.
On a flat Earth model, there isn't such a thing as a boundary between the northern hemisphere and the southern hemisphere, is there?
The Tropic of Capricorn would be considered that boundary.
Yeah. So, but on your model, one would expect that explains why there might be vortices, but you would expect the difference between one direction of vortex and another to be variable. How does it obey this line halfway between the two?
It follows the jet streams. I don't know how.
Yeah, but the jet streams aren't going to be exact line. It'd be incredible to believe it was an exactly straight line at all times.
No, it's not straight lines. Let me just see if I can find, because it's difficult to.
But you're accepting that the vortex is in the opposite direction, and
yes, I accept that, but I don't think it's due to Earth curve. I say it's due to the physics of how the storms move the air. So just like you take your hand through water and you'd swip your hand and it makes a vortex this side, and the other side it makes a different clockwise vortex. That's because it's the movement of the current. So those jet streams that are pushing it that way through the topography, and because it's hot and cold air that's trying to make it onto makes the hurricane, it's forced into that direction. So it's almost funneled, you can say.
Yeah, I completely understand that. But what I'm not quite clear on is that if that was true, maybe I'm not explaining it very well, but you might expect it to roughly be all in one bit and then the opposite direction another bit, but you wouldn't expect it to be a perfect division where the Coriolis can never cross the equator.
You can because it funnels out. Just like let's for instance imagine a 10 lane highway, okay? Yeah. And you got the middle rows are all going straight, and the outer rows, as it's going, they flaring out.
Yeah.
So they're going in the same direction, but the outer ones are flaring out. So that wind is pushing that way. So these flaring out ways have to spin that way. The flaring out that way has to spin that way. The equator is just that. Just like it's showing here on, you can see here, this is the jet streams. That follows the same paths on your globe.
Yeah, I think it's just going to be under the category of it might be possible to explain it on a flat Earth, but it's more tricky. And on the globe Earth, it's just more, it's an easier explanation, I think.
No, you see the globe Earth, that's the saying. The globe Earth uses it by saying Earth's moving. Where the flat Earth uses it by saying, no, the Earth's not moving. It's the air that's moving due to physics.
Sure. Yeah. So going back to the water, sticking on a ball point, that if I understand it right, you're saying that's a straw man. That's not actually what a lot of flat earthers believe.
I think they do it as a joke.
Right.
I don't agree with that argument, because if you understand the globe physics, it doesn't. It's just a joke. Because you would understand the Earth as a larger mass compared to that little ball demonstration.
Yeah. Sure.
So I don't agree with that. Although I do laugh with it because I see it as a joke, but I don't agree with it, like I said, because I understand the physics behind it.
Sure. Okay. Well, I think I've got a couple of points, but they're not really take us that much further.
But yeah, something I also want to say on the Coriolis. You do know the difference between the Coriolis effect and the Coriolis force, though.
Yeah, I would imagine they're different. One's the force and one's the actual effect.
So would you say that the hurricane is based on the Coriolis effect, or it's based on the Coriolis force?
Well, that I don't know. I don't really know enough about hurricanes and how they form.
Yeah, because when we say, for instance, Coriolis effect, it would be an observed phenomena. You would actually see it have an apparent deviation. So it's not taking an actual deviation. It's only appearing to take. So what happens is you would be on the moving reference frame, the non-inertial reference frame, observing something in the inertial reference frame, taking a linear path, having an apparent deviation or drift. So like you'd be on a roundabout and someone throws a ball, you would see that ball, according to your position as you move underneath it, take a curved path, but it's actually taking a straight path. That'd be Coriolis effect. Now, the Coriolis force, for instance, we put that ball on the ground of that merry-go-round and you move it. That ball will be rolling due to the forces of that fictitious force spinning. So they're claiming the hurricane is formed due to the Coriolis force.
I see. Yeah.
Yeah. But when we talk about Coriolis, and for instance, now you would be able to see deviation if it's claimed to be that way. And that's why I brought Globiolus up earlier, because you guys require the air to be velcroed to the Earth to move. As you said, it just moves in different, it moves with it, with momentum. But if you do this, you don't have two separate reference frames. So therefore, you can't observe Coriolis effect. So it either has to be there or it doesn't be there. So
yeah, on a globe Earth model, if the Earth suddenly stopped spinning, you'd have
would be dead.
Yeah, we'd have really strong winds and everything would get ripped up because the air would carry on. And it's not exactly the same, but this is the whole point. This is why you've got weather systems, because air is fluid and it doesn't move in a rigid way like a solid does.
Well, how would you explain the tangential velocity though? Because with altitude, it would have to spin faster at higher altitudes than lower. How would you explain that tangential velocity though?
I would explain that I haven't come across that before, but I would, just thinking on my feet, explain that by the fact that the heights that you're talking about aren't that significant, because the Earth is their circumference is something like 24,000 kilometers, isn't it, at the equator? And what height are you talking about? You're talking about what, 7 kilometers or something?
Well, let's put it this way: if you're in an airplane and you take off from the ground, okay, and you get to, let's say, 35,000 feet, you would agree at 35,000 feet, you would have to be traveling faster to keep tangentially with the ground than when you were on the runway, because you further away, your radius has increased.
Yeah, but it hasn't increased by much because it's 24,000 kilometers. It might even be miles. I'm not sure which one it is, but it's 24,000 circumference at the equator. And if you're only 9 kilometers up, which I think is what domestic flights are, that's quite low. If you imagine, you wouldn't expect that to make a huge difference. I think that's just a mistake of not understanding quite how big the Earth is conceptually.
Yeah. But you see, because what I'm trying to
Sorry, go on.
Sorry, because what I'm trying to get is, if, for instance, the Blackbird, it flies at 70,000 feet, okay?
Yeah.
Where there's hardly any air.
Yeah.
But it's claiming to have the momentum with the air and the spinning Earth. How is it keeping momentum if there's no air to push it with the Earth? And how is it increasing tangential velocity, which actually goes against the first law of thermodynamics, because you would have to put more energy into the system.
Yeah, it doesn't need air because it's traveling not so much because it's pushing against air. It's traveling because it's pushing hot gases out of its engine, and that has an equal and opposite reaction on the plane, pushing it further forward. Now you notice this with like the ISS, that's rotating at a very, very fast speed, and obviously in orbit, the further you are away, the faster you have to travel to maintain the orbit.
Yeah, but what I'm saying is, now, let's say the Blackbird is going in the opposite direction out to Earth's rotation. So it's going against Earth's momentum. And now the Earth and the air is moving opposite towards him. So that momentum is now not stored with the plane. Why don't we see Coriolis effect with that plane?
Because the plane's not air, I would say. It's a solid object with its own thrust.
Yeah, but that means the plane should be flying faster against the rotation to get to its destination than the other way, because it has no longer got the conserved momentum, because he has attributed a force now, because to conserve momentum, unless acted on by an equal or unequal another force. Now the plane has a force because it's going in the opposite direction. It is too high up for the air to keep it going, because people explain it in like a river. If you're in a moving river, you can swim, but to people on the side of the river, it looks like you're swimming backwards. Now, if you're in a river with no water, it can't pull you backwards because the air is too thin. That's what I'm saying. So the plane would be flying and it won't be able to conserve momentum because there's nothing to keep it pulling the momentum. It's got force attributed in the wrong direction. So therefore, to us, the plane should get to its destination much faster, because the Earth would be rotating underneath it while it's going.
I think the bigger factor would be the airflow due to weather, winds and stuff. So if you've got a tailwind, for example, the flight from New York to London tends to be a lot quicker than the flight from London to New York. The prevailing the prevailing wind, which is due to the rotation of the Earth, is a westerly, and so that's going to overtake the fact that the plane would be very slightly higher. I mean, it's a very small amount, isn't it? When you've got the Earth that's big and it's only 9 kilometers above the surface, that's going to be the bigger effect. I mean, I think you're right that it's traveling. Like if it was circumnavigating the globe, it would be taking a longer path, 20 kilometers up compared to 9 kilometers. I mean, that's a given, isn't it? But the difference is actually quite small when you're only those sorts of distances. You'd have to be sort of 60 kilometers up for it to make a big difference.
Yeah, because when I was looking at, for instance, remember Felix Baumgartner when he did the Red Bull jump? He jumped over New Mexico, and the thing is, when he went up, he was in there for a few hours, and then when he jumped out, he landed practically where he jumped.
Yeah.
So if Earth was rotating, and remember how high he was, there was hardly any air to keep him to follow that momentum. yet he landed where he jumped. So that would show against Coriolis. That would show
But
against
wasn't he on something that he was surely on something that was moving?
when he went up. He was in a balloon, but when he jumped out,
But he would have had the same momentum as the balloon when he jumped out.
but that's the thing. There is no air where he was. It was too thin, so he couldn't keep that momentum with the air.
No,
Because
but he doesn't need to.
the air would be. It's like the river example. You need the medium to help keep the momentum. If the medium is not there to help keep the momentum,
Yeah.
because now he's got another force. Remember, when he jumps out, he's got another force.
I'm not sure I agree with that, because momentum isn't dependent on the medium. So if the balloon is traveling, if it's rotating, then when he jumps out, he's got the same momentum as the balloon had, irrespective of whether there's any air. In fact, if there's air, he keeps more of the momentum because he loses less of it to friction. So when he's got that momentum already, and then he's landing, and the Earth is moving with him. So he's not going to land exactly in the same spot, obviously, because of weather conditions, wind, and all sorts of things. And possibly some of that is due to the movement of the Earth relative to him.
But I think you misunderstand what I'm trying to say. Because how high he was, there was hardly any air there. He had to even wear a mask so he can breathe, because it's very low vacuum. It's practically space, they claim. So if he's so high up, now the balloon went up, kept with the momentum, you can claim. But as soon as he jumped out of that balloon, he cannot conserve momentum, because he has now a new force attributed to him, because he's falling down.
No, but I'll stop you there. That I don't agree with. So if he's got momentum in the horizontal direction, vis-a-vis the surface of the Earth, that carries on. So the Earth is moving this way, he's moving with it because he's got that same momentum as the Earth. The fact that there's no medium at that height actually helps him conserve that momentum. Yes, he's moving down, but the downwards momentum is perpendicular to the horizontal. And if a force is perpendicular, it doesn't actually detract. So it doesn't take anything away from his horizontal. So if you remove air, just imagine there's no air, and you're moving at 100 miles an hour through the air, you will be falling with gravity. But because gravity is acting perpendicular to your horizontal motion, it doesn't actually slow down the horizontal motion. So the horizontal motion just continues. I think that explains why he landed. That's nothing to do with whether.
He landed actually a bit opposite to Earth's rotation. He landed eastward, not westward there.
Yeah, but that could be down to air currents and wind and all sorts of things.
So it's just interesting.
Yeah, but interestingly enough, it doesn't. Whether that's true or not doesn't actually make any difference. So whether that would work on both a flat Earth and a globe Earth, because if the Earth was flat, he'd also have the same momentum and land in the. Well, actually, no. Maybe suppose the whole thing doesn't work. The whole thing cancels each other. It cancels out, doesn't it? Because on a flat Earth, it wouldn't be moving. He'd be stationary, jump out, and he'd land in the same spot. If it's a globe Earth and it's rotating, you see the same result. So it doesn't change the position either way. Both result in the same thing. He'll land in roughly the same, not exactly the same spot, but roughly the same.
That's quite interesting.
Yeah, weather conditions and stuff. Actually, just something I said was wrong. I think I said that the lower you are, the slower you need to rotate. It's actually the other way around.
No, it's correct, because tangential velocity. Because with the higher you go, the tangential velocity has to increase. But that's what I'm saying. It actually defies the first law of thermodynamics, because it means you're adding energy into the system to keep spinning faster.
But not on the. I don't think on the globe Earth that's the case, because the theory is that when you're in orbit, what's happening is you're actually constantly falling to the Earth. But you're moving horizontally so fast that you're falling with the curve. See what I mean?
You're falling in a parabolic.
Yeah. So you never actually go down because you're following the parabolic. So further up you are, the less fast you have to go to follow the parabolic. The parabolic is tighter the closer you are, because you have to do a tighter bend, right? So you've got to travel even faster. So you could, in theory, if a bullet was fast enough, and there wasn't any air resistance, it could rotate, it could orbit the Earth, but it would have to travel bloody fast, wouldn't it? Because, because it's so close to the Earth. Yeah. But in theory, it could, if it was fast enough, and then there was no air resistance, it would.
So you're claiming Superman can't turn back time?
I really don't. I think going back in time is an interesting one, because you'd actually need higher than infinite energy, which is quite difficult, because you need infinite energy to reach the speed of light. To travel back in time, you need to travel faster than the speed of light. But on our physics model, traveling faster than the speed of light would actually result in you going back in time. But no one can prove it, unfortunately. You can go forward in time. You can do that, because if you travel at, say, 95% of the speed of light, time dilation is such that relative to another observer, time for you goes so much slower, such that you would age a lot slower than somebody else. I mean, you wouldn't feel the difference. For you, it would just be normal.
But for them, yeah.
Yeah, and interestingly, it's not just time that dilates, but space. So that what you would observe is the universe would be shrinking, but only in the direction of travel. So if you're traveling this way, things would contract like that. They'd be the same height, but they would contract. And if you were traveling at the speed of light, actually at the speed of light, the whole of the universe would be shrunk into an infinitesimal.
Yeah, you're kind of like explaining a black hole when you get to the event horizon.
Yeah, you would be everywhere in the universe at the same time. That's the way
it would be like what I explained if you get into the event horizon of a black hole. To the observer on the outside, it would seem as if you're standing still.
Yes, and you would get redder and redder and redder until you fade away because of redshift, which would happen to your light. Mm-hmm. It would be elongating the photons. And if you elongate photons, well, you get something called a redshift, which is going from a blue wavelength to more a red, infrared, microwave, radio wave, etc.
So you can see, I do enjoy my sci-fi, but you see, this is the difference between how I think flat earthers and globers think differently. Where we see it as, it's all just fantasy. It's not being shown true. You need it for your model, but in your paradigm, you obviously it exists because it just follows the globe physics. But where we see it as like, none of this to us, it's Narnia. It's just story, cool story, bro, kind of thing. So I think that's why it differs. But that's why I enjoy actually having a discussion with you, because we're able to see both sides of the arguments.
Yeah, exactly that. And I think that's all it comes down to, is that a lot of these things that are in favor of the globe, it's not that they don't work at all on a flat earth. It's just they have to come up with an explanation, and each one on their own doesn't cover it. And it's a personal choice, isn't it? That do you think that the evidence stacks up in favor of one, or does it stack up in favor of the other? And you put different people in the same room and they'll come up with different viewpoints. And that's what makes it very interesting, that we're all different. If we all thought the same way, wouldn't it be boring?
Yeah. I think this is cool though.
Oh, definitely. Yeah. And it's definitely insightful. And I think a lot of the arguments in favor of flat earth are questions that are reasonable questions to pose. Like, why? So if the earth is a sphere, how come this and how come that? Which are very good questions to ask, and it's a very healthy thing to do, to think that way, and to be curious about the world rather than just accept it. That's what we've been told it's today.
Yeah. Because I am still under the comprehension, if I wasn't taught it was a sphere, I don't think I would ever think it was a sphere.
Oh no, you wouldn't. No, and I'm sure animals don't think that. Even relatively intelligent animals like chimpanzees, they probably don't think it's a sphere at all. They think everything's flat.
I don't think they care.
They don't care as long as they get the banana, right? But yeah, so it's all, and they say the debate will carry on. I think the internet's given a new lease of life to the flat Earth belief.
Oh yeah,
because I think what the internet does is it introduces people to each other that wouldn't otherwise know they were in existence. And if you were isolated, you might have been browbeaten into just believing the consensus. But obviously, you're able to have a channel and you're able to have a community and see that other people think the same way as you.
I agree. But like I said, this is why I don't call like you anti-flat earth. You're just a normal glober, because your whole demeanor is different to anti-flat earthers, as we call them.
I think I mentioned to you on the email that I saw your debate with the other chap. I won't name him or anything, but he got so angry, didn't he?
Hey, actually, that was one of the most tamest debates he's had with me. I mean, you should watch a lot of my debates. People get very triggered that they wouldn't let me talk at all.
Yeah, I don't. There's no place for that. I don't understand that. You know, if you don't agree with somebody, there's no reason to talk on top of them or call them stupid or just.
But it's entertainment, though.
Yeah, I suppose it's more views. Maybe more views than. Yeah.
But I enjoyed this. I'd definitely love to do this again.
Yeah, absolutely.
But if you have any more just questions, you can also email me and stuff, and I'll definitely, because I have looked into this for a long time, and I think we get arguments from left, right, and center everywhere that sometimes you'd never heard of an argument somewhere. I don't know. But
there's always a new one. When I debated Sov, he came up with a few new things I hadn't heard, and you've come up with a couple of new things too. I don't know. Do you want to do you open your forum up to comment, questions, and that sort of thing?
Yeah. We actually got a super chat.
Brilliant.
Let's see what they said. So let's first say, Roger, thank you for gifting a membership. Really appreciate it. And the Mega Worthy for $5 super chat. He says, so the argument for globe Earth is it would behave exactly like a flat Earth? Is this gonna present proof or more conjecture? I think it's more a statement than a question.
I was struggling to understand the question.
Yeah, I think he's saying, are you going to present or anything, or is it just more just accept it because globe?
If he's asking, I think the difficulty is that it's very difficult to change somebody's mind. And I think it would be very difficult for somebody to persuade you that things are different. And it would be very difficult for somebody to persuade me. And I guess maybe a good question would be, what would make you change your mind? Maybe something for both of us to answer.
Yeah, definitely. I just asked anybody in chat if you have any questions. Be sure to know. PJ, you can also ask. You are in already, so. But yeah, I think this was very respectful, and I like you, man. It's not because you got the same surname. It's because
and the same first initial.
Yeah, I'm Keith Reynolds. You Kent Reynolds. How's that?
Yeah. I did say that at the start, didn't I? Yeah. No, I just think it was a cool conversation again. Like, so it's really pleasant, and that it's normal stuff that we usually talk about, but in a better manner. You know what I mean? Usually there's arguments left, right, and centre. Straw man's being thrown all over the place. Ad hominems, all that kind of stuff. But no, I just think it's been a pleasant conversation. I've got no questions and such, but fantastic.
I actually got a question for you, Kent. What is your thought on level? How were you taught what level is?
I think level is it's something that's with respect to the ground, isn't it? So something's level, like a spirit level, for example, it will show you how level you are. I mean, it's relative, so the ground has to be level as well. So if the ground isn't level, your spirit level will be telling you something that's actually wrong because it's based on gravity.
But
the air bubble and
of course. But like the first meaning they've got for level now, no point higher or lower than the other, and the second meaning, as in the globe version of it, where it's parallel to the Earth curve, totally contradict each other. Totally.
Mm-hmm. Jeff Conkle sent a $2 super chat. He says, Kent, I think you are more on the fence now. Thank you very much for the super chat, Jeff. You rock. Yeah, because if you look at level, you would agree that it requires a horizontal.
Yeah, I mean, that's the definition of it. It's level with respect to a horizontal.
So that's why I don't understand how the globe can claim level on a globe, because a horizontal can't curve. So, but I mean, you probably saw my argument with FTFE anyway in my opening statement, and that's I just wanted to find out, what are
Yeah,
your thoughts on level?
my thought on that is it's all about scale. So on things can look a certain way at different scales. So on our everyday scale, which is meters, maybe kilometers, but mostly meters and centimeters, then at that scale, you can just ignore the curve because it's too slight. And therefore, you can just treat the Earth as flat, and level is just level relative to the ground, provided that the ground is level. And so that's why your spirit level works. If you had a giant spirit level that was, like half the diameter of half the circumference of the Earth or something, then that's when you would have the problems. But on your everyday scales, you wouldn't present a problem. And that's consistent with both models, because that is, I think flat earthers would have to admit that is, if the globe Earth is true, that's what you would observe on our everyday scales.
But I wouldn't say the horizon the alleged physical high horizon being at 3 point whatever miles out is that slight. To be honest, I think that's very small. If you're seeing curvature that close, 3 miles out, I don't think that's that slight, to be honest.
But you're not really seeing curvature. What you're seeing is the ground falling away from you. It's not the same as observing curvature from above, which takes a much higher height. I've seen this in the memes, internet. Oh, how come? That's the argument, isn't it? Oh, how come you can't see the curve from 9 kilometers up, but you can see it only 3 miles away?
Or on your x-axis, you don't see curvature left to right.
It's a brilliant question, but it is answerable.
Okay, cool.
Janus, sorry, man. Janus he says he wants to ask a question. How's it going, man?
Hey, how are you? Nice to meet you, Kent. I'll make a statement, and I would like to know what you think about it. From my perspective, you can't change anyone's perspective, anyone's mind, because truth can't be told. Truth has to be realized. So my question to you is, what kind of evidence you would consider to become flat earther?
Yeah, it's always a very difficult question to answer, because you have to imagine what it would be. I suppose probably lots of small bits. I mean, if there was a real evidence of a conspiracy of some kind, that would obviously help. Somebody coming up with some kind of experiment that debunks everything, and that goes viral and is repeatable, I guess.
I think there is such evidence, if you would like to consider it. Flat, if you could show the disappearing ships behind the horizon.
Yeah.
So this one possibly could convince you. Do you have them?
Convince me in which favor? In favor of a flat Earth?
In favor of flat Earth, yeah. That is not a globe, because ships do not disappear behind the curvature of the Earth.
I think there's too many explanations on both sides of the argument for that to be conclusive.
Yeah.
Because there's explanations when globers say it disappears bottom first, and that supports the curve, then flat earthers have an explanation for that, to say you can zoom in and it might be the weather and it might be the waves and the tides and so forth. So you're never going to get a complete resolution to that. I don't think that alone would be enough, because there's too many arguments, if you see what I mean, on both sides.
Because I wanted to bring the black swan up, but we didn't get to it. So
just saying it's like black swan.
I actually wanted to ask: have you heard of the black swan before, Kent? Oh, you muted me.
I haven't, but I saw a comment saying Kent asked about the black swan or something.
Yes,
yeah. I'll actually explain that to you now. I just want to read this. Roger Little, he says, "Thank you." He says, "Kent, I hope you look a little deeper." I think Kent is looking deeper. That's why he's having these discussions, just like all of us. And I think you're awesome, man. Keep on doing what you're doing. And don't fall under peer pressure. Just do your thing.
I think he's been fairly open. Definitely.
But you know what, Kent? You are going good way. I can see it. And I think in a short time we see you and we welcome you in the Globe Earth community.
Brilliant.
Let me see. I'm going to bring up the black swan on... on QB site, because it explains it the best. Okay.
I give you one example, one truth. Probably you can see that people are leaving globe Earth and moving to the flat Earth. But do you see people who were flat earthers and become again globers?
Black Swan 2020.
Okay. Well, the black swan here. This is an observation done, which shows two platforms. They are measured distance, 6.2 miles and 9.4 miles away. Okay.
Yeah.
Now it gives a modus tollens based on your globe's radius. Oh, sorry, I was just going to say thank you, Theo Megawary, for your $2 super chat. It says shout out from crew at 24/7 Flat Earth Discount. Woohoo! Shout out to you guys at 24/7. You guys are awesome. They do so much. You should actually go chat on 24/7 sometime. Kent,
Mm.
oh, do you have Discord?
No, I haven't.
If you get Discord, you should go look at 24/7. It's also a Flat Earth dedicated
Okay.
Discord, and they talk a lot. They always have people open there, and they talk a lot about the Flat Earth and discussions and stuff. I think you'll have an awesome time discussing with them. But thank you very much, Theo. You rock.
Definitely. We used to use Discord a lot, didn't we, before we went on to
Mhm.
stuff like that. But beware that, I mean, it's as good as there is good channels and like
Yeah.
that, there is a lot of trolls in Discord. Just to
Yeah.
you know.
Okay, so the modus tollens based on your radius value. Okay, so it says if P, then Q. So not Q, therefore not P. So it's just setting up a logical deduction. So if the Earth is a sphere with a radius of 3,959 miles, that would be P. Then every horizon distance measurement must be no more than 1.225 times the square root of the observer's height in feet. That would be Q. That's the observation. That would be the geometric horizon. Okay. That's according to the curve calculator. So if we say it's not Q, therefore that distance is not 1.22 times the square root of the observer's height in feet, therefore it can't be P. Therefore the radius is not 3,959. You agree with that? Because it's just a modus tollens. It's just a if or not statement. You'd agree? So if we look at this observation, okay, the horizon based on a 1 foot height can only be 1.22 miles away. The issue with this observation is platform heel height is 6.21 miles away. Platform habitat is 9.41 miles away. The horizon is much further than that. Done another time. See where the horizon is.
Yeah.
So in other words, according to your globe, the horizon should have been on this one 3 miles away, on the other one 1 mile away. But the horizon is way past 10 miles. Now the argument we get, most of it, is refraction.
With the crane arms.
I was about to say, wouldn't refraction answer it?
But there's an issue with that. Even with your terrestrial refraction, it's way, way too high for the globe. It pushes your radius out something like to what? What did Adam work it out? To 250,000 miles?
Well, that's what, 10 times?
Yeah. It pushes it out magnitudes higher. I'm going to actually put this link for you as well if you ever want to look into this. But there we go. But that's what they call the black swan. In other words, we see the horizon too far. And even observations we've seen, I don't know if you've seen, not behind the curve. What's that other one where they try to show, where they put Mark Sargent and they take the boat. They take the boat and it moves away with a flag, and they say you see the horizon is blocking the boat.
Can't remember the name of it.
If you look on that video, the horizon is past that boat,
Mm-hmm.
but yet it's getting blocked by the water, but the horizon's past. So if horizon is claimed to be Earth curve, how is it being blocked?
Yeah.
It's a good question. Worth to consider.
I mean, I think these are they're not they don't prove a flat Earth. All they do is they question at one aspect of the globe Earth theory, and it's another well, how come this argument? And there could be an explanation for why at that particular photograph that's what's been observed. But you would see it everywhere, wouldn't you? Surely it would be massive news if you wouldn't just see it on one occasion. You'd see this on everything. And everyone,
you see how,
yeah.
sorry. No, you see how I would see it is it shows our argument that it's just optical, not physical, and it shows against the globe. So yeah, I wouldn't say it proves a flat Earth or anything, but it definitely shows the geometry is not working for the globe at all.
But only on those examples, because there are other examples where you do see the ship disappear bottom first.
Which all comport with
explain it purely by waves or tides and wind and stuff.
I agree, yeah. But I still hold to it's optical.
But this is the problem: is we can be experiments can be deceived by variables, refraction and perspective, and all sorts of things. That's why we've got people who are flat earthers and we've got people who are globe believers, and it's difficult to resolve it because one person will come up with one thing and then another person will say, but it's just this and it's just that, and sometimes it's okay, we haven't got an explanation for that, but that doesn't necessarily prove that the other side is right. Just because there might be a problem with this particular experiment.
There is another one argument, okay, we can take into consideration water and the waves and the air and so on, but people did as well experiments on the flat surface. It was on the desert, the biggest white desert in the world. I just can't remember the name. So there is no waves, and still supposedly items disappear bottom up. But later, when you zoom in, they're appearing again. So, anyway, I think you have missed my question. Before I ask you, probably you can see that people now moving from not a lot of, but some people are moving from the globe Earth model to flat Earth. You have observed it probably. This.
Yeah. So I think your point is that more people move from globe to flat Earth than move from flat Earth to globe.
But there is no people moving from flat Earth to globe. Do you know any examples? Ask yourself a question.
There might be some, but I can't give any. Okay. But I think that might be because the flat earthers that you see are the ones that are staunch believers in it, that go onto YouTube and are interested in it. But there might be a lot of people that don't know the globe Earth model very well, and might have thought that the Earth was flat due to not being educated about it. And they may then become a globe Earth believer if they then take a physics course, for example. So you can get it that way. But I think the answer to your point is that it's about the psychology of people that believe in flat Earth, because these are people who are naturally very curious and skeptical about you have to be skeptical about mainstream, right?
Yes.
You're a flat Earth, you have to believe that you're being lied to by a large number of people, and
well, not actually.
Well, so what could it be then if it isn't being lied to? Or maybe lied to the wrong word. Maybe it's being misinformed.
Flat, are you there? Oh, he was frozen.
Is he frozen?
Yeah, he'll come back. That happens quite a lot. It'll come back.
Oh, okay, right.
Usually.
I thought it was unusual for him not to have something to say on it.
Sometimes he does have it's a South African, and so they've got what do you call it? Periods where the electricity goes off, load shedding. I think it's called load shedding.
Oh, okay, yeah, sure, yeah.
I don't think he's having any of that at the minute. I just think his signals dropped for a bit.
Oh, sure, yeah.
If he can't come back, you'll say it, and you'll say, "Oh, it's dropped completely."
Yeah. I seem to have lost
I think what you just missed was what I was saying was that necessarily you'll probably get much more people moving from globe to flat Earth than flat Earth to globe, because you have to be somewhat of a skeptic to be a flat earther. And it's that kind of mindset. And if you've got that mindset, you're unlikely to go back to mainstream. You're very I like to say, oh yeah, I think it's I was wrong. So that's why you probably don't get much moving in that direction.
I can agree to that. I'll put this link as well. It's Rob Skiba's. I don't know if you know who Rob Skiba is. So he's actually a flat earther that died recently a few years ago.
Yeah.
He also has a very big channel. This is a demonstration he also did with using a Fresnel lens to explain the refraction, how it causes things to look like it's going down over a curve. This is on a marble top, so it is flat. Watch out what happens when he moves it away. It's quite interesting.
What's he doing? He's moving it. It looks like he's moving it down, but he's not. Is he? He's moving
He's moving it away. He's got a Fresnel lens there to show the effect of refraction.
Oh, I see. It's the refraction. I see.
So it gives the bottom up obstruction. You see.
Yeah, I see that. Yeah.
It does
But I put the link. I'll put the link in for you if you want to go through his channel as well and go and see things.
Yeah. By the way, these things that you're putting in the private, is there anywhere where will I lose all that when I come out, or was there any way to get that?
Must I email them to you?
Oh, brilliant. Okay, thanks.
I've just what I usually do is I just click on them and then bookmark them. I just put a star at the top, bookmark them.
Oh,
But
brilliant.
it's fine. I'll email it to you.
Yeah.
No
Thanks.
stress, man. And you can always ask me if you need anything. I'm more than happy to accommodate you. Fingers
Rob
in my-
Skiba was good, yeah. He died young as well. He was in his 50s, wasn't he?
Yeah.
He was 50s. Yeah, he was a good representative of flat Earth. And
Is there any other questions you want, or
I'm good.
think-
Good.
Kent?
No, I think we've covered pretty much.
I think this was great, though, man.
Yeah.
I really enjoyed this discussion. I think this is how it should always be.
Absolutely. It would be a lot easier if it was all like this. If it was like this all the time, sorry.
It's refreshing. Let's put it that way.
It is. It is. That's hence why I reviewed it straight after because Soft came in and says it was really pleasant, and I couldn't believe it. I was like, I've got to see this.
You see that, Kent? I wanted to review it, but after watching you guys' discussion, I was like, what am I going to review?
I couldn't add to it. I just had to keep saying, yeah, this is a good conversation. That was my review.
I was flattered. The nicest comment I saw in the comments was said that Kent's too nice to be a globe earther.
Yeah, there you go.
I took that.
It's well said. Well said. I agree.
That's it.
Yeah, the thing is, because in this arena, there's a lot of negativity and so that's why I said it's definitely refreshing, man. And I think you're a guy we can easily get along with.
Brilliant. All right. Yeah. Well, thanks again so much for having me on on your channel and show and everything.
Anytime, man.
Absolute pleasure.
And as soon as you do start your channel, please do let me know.
I will. Yeah, I'm tempted to start it up now. But if I do start one, it won't be, sort of like an anti-flat earther one. That's definitely not what I want to do. It would be more something where, like you've got, like invite some debate and spark some interest.
That's about it.
Exactly. Yeah.
Yeah.
All right. Well, I think that. Thank you again, and I think I'll leave you. So have a great. I don't know. You're on the same time zone as me, aren't you? So same.
I am 2 hours ahead, so it's 11:45 now.
So it's even later for you than me, probably. Right. All right. Thanks again. Cheers.
Nice, bro.
You too. Thanks, Kent. Appreciate you, man.
Thanks, Kent.
Blessings.
Great interview.
Yeah, I think it was awesome. I'm going to put the link in the chat if anybody wants to come just chat for a bit.
That was great, man. I mean, perfect. I mean, you can't ask for a better conversation than that. He's wrong, but you can't ask for a better conversation. You know?
But you see
But I see potential. He might become flat earther.
Yeah, hope so.
For now, not
what
yet.
I like about him is he's honest.
Yes.
And even if he doesn't change his mind, that doesn't
Exactly.
mean anything. Everybody can believe what they want. This is why I say there's a difference between people like this, a Globian and an anti-flat earther, where anti-flat earther hates everybody just because they don't believe what they believe. A Glober It's like, yeah, okay, I see your point. Yeah, I don't agree with you. Yeah, move on. There's no bigotry or hard feelings about it. You know what I mean? Good
That's
guy.
exactly Dr. Mabuse. Dr. Mabuse is a global in chat, and even he's saying that was good. That's what I'm saying. It should be like that between flat earthers and globers, just to talk about it. Shouldn't be like how it is, all the animosity. But I know we're always going to have that, aren't you, flat earthers?
Mhm.
I know
No,
we're
I think he's an awesome guy.
too right, too right.
Yeah, definitely he is. I have uploaded this video with the buttons on my channel on Odyssey. That's a great one.
Yeah. Well, I did put the link in if everybody wants to come and discuss. Ugh.
Yeah, I had to ask you,
Yeah.
if I can ask question, because I just didn't want to interrupt your interview. That wouldn't be fair, So I just that's okay. So just to ask someone.
No stress,
I don't
man.
want to impose myself.
Yeah, that link I put in there. It's the flat Earth device. It's got a wee disc on it. It's like a old school sextant. It's mini, and then it's got a
Oh.
fold out disc on it. It's really cool. I've seen it on Rumble, and I showed it on my live earlier on the same channel. It's called Pray for America. There was an 8-year-old girl presenting flat Earth as a school project he even presented the egg experiment. No, it's Sandra's Sleeping Warriors egg experiment. She presented that on a whiteboard and everything. I wouldn't show it live because obviously it's a young girl, but I thought it was really cool. You know what I mean?
Yeah,
But
I
yeah,
just yeah,
this other one is the flat Earth device. If you want to show it, it's only about a minute long. It's pretty cool, I thought. But yeah, I just thought it was cool that it was an 8-year-old girl teaching flat Earth. You know what I mean? Showing as a school project. But this is just that's the device navigation.
yeah,
It's really
yeah.
cool.
I just followed the channel, so
Okay. Oh, what
yeah,
the Pray for America?
yeah.
Yeah. Yeah, it looks
What's
pretty
up,
good.
Jeff?
Pretty
What's
good.
up, Jeff?
Yo, how's it going?
Good. So what were your thoughts?
It was actually very cordial, and respectful between both of you, and it was like I really enjoyed it. Actually, it's like a breath of fresh air from all the
I
other
agree.
ones. So
But I observed some mimics on your face, Flat, when he was saying some stuff, it was definitely debunked a long time ago. But you still believe it. It was like, oh no, he's using this argument.
Yeah, but there's no need to really,
No, of course not, of course not.
fight or anything.
It's just involuntary, because okay, I know it, I already know it, I know how to respond, You can see the smile, not smile on your face, Okay,
Well,
I know how to rebuttal it. Yeah, straight away.
yeah.
That was
Well,
nice to see.
but it is interesting to see, like a few things he didn't know about. So you can see it's
Definitely
ticking in his head,
respectful
and I think if he
wanna
does
learn.
go and look it up and look at it,
Mhm.
he'll obviously see a lot of the things, excuses from the globe,
Yes,
but
yes,
he'll also look at the other side of the argument.
yes, and he's willing to learn. That's the thing. He's not like
Quite,
disregarding all the arguments straight away from the get-go. He's looking
quite
into it,
surprised.
so it's great. That's great.
I'm quite surprised he hadn't heard of the Black Swan, though. Quite surprised. I can't believe how old the Black Swan is now. 4 years.
Yeah.
4-year-old man.
Can you believe it?
Yeah.
On my channel Odyssey, I have interview. I think it was maybe Michael Tellinger making an interview with the woman, 104 years old.
Oh, yeah.
Flat, you frozen again.
Oh, wow.
In the nice pose.
Nice pose. He's doing the thinking
Anyway,
man.
oh no,
He's doing
and the question
thinking
was, what is the shape of the Earth? And she said it's flat because in her school, all books were saying that the Earth is flat. It changed later.
That's Odyssey. Sorry. This is Giannis's link for Odyssey, guys, in chat.
Thank
what were
you,
you
PJ.
what were you talking about? It's like we're changed in books.
Yes, because around I think it was 80 years old. All books still were saying that the Earth is flat,
Yes,
but later there was a shift, and it was changed
and
to
that was
globe Earth.
And that was because of the Rockefellers
Yes,
coming in and
indoctrination.
changing it all in 1920.
Yes,
Yeah.
and you know
Yeah.
how it happened exactly, how they influenced. Do you know the backstory?
Not totally. I know no parts of it. But
So they were saying, they were approaching schools and they were saying, we bring a lot of money, but we have to
Yeah.
have people from our side in your school boards. And they were saying there will be no control as I want, they will be only looking. But because they were bringing money, they were in control exactly. And they were saying what will be the curriculum.
Okay. Well, I don't know what's wrong with my internet.
Yeah, mine
Keeps
was
going
great.
out for some odd reason.
a friend of mine has an encyclopedia from 1940s.
Mine's
It was the
been
1940s, and it actually says that the airplanes couldn't fly above a certain height in Antarctica.
Yep, it will hit the invisible dome. Exactly.
And it's like, okay.
It gives dimensions and everything at latitude.
Wow.
Yep,
Yeah.
seen that.
Yeah. Remember, guys, tomorrow morning, Luke and I will be having a special show.
I won't be
So
watching.
make sure to see that tomorrow morning. It's going to be exciting at 8 o'clock Central African time.
I will definitely pop in, but I'll have it on mute so I can't hear it because I'll be covering it not Tuesday but the week after. Well, no, 2 weeks after because I'm on the third one tomorrow. I've done the fourth one. Luke doesn't want me to do the fifth one that was meant to be with Jado because
Well, Jado, yeah, because we had that other guy come on.
Yeah, he doesn't want me to do that one, so I'll just do because you've done 5 now. You're about to do the 6th, so I'm just about to cover the 3rd, but it'll be my 4th one covering it on Tuesday.
Well, we're still gonna do a lot more of these.
That'll be cool. I'll cover them all the time, man.
Yeah, it's really
Because
cool.
it's pretty. It works out well because I'm covering really for you on a Tuesday. It's one of your videos, and it's Luke as well, who's I work on well with. So I love covering it, and it's what I do. It's what I do on my channel, covering like things like that. So it's good. Works out well.
But yeah, I would hope to have a discussion again with Ken sometime, and then we can talk about like the Foucault's pendulum and stuff like that as well. I think that can be quite cool. So yeah, guys, just want to say thank you to everybody for coming. Appreciate all the likes, appreciate all the super chats and the membership. Thank you very much. You guys are awesome. But please do share the show because it really, really does help. Hopefully, I'll see you guys tomorrow morning on the other show. Any closing statements?
Yeah. I mean, I can only just say that was ace, cordial. It was pleasant to listen to. Rather than having to go like screeching and all and getting ready to come in because you want to swear at them and stuff like that. Just cool. I could just sit back and chill. That was it. You know what I mean? It was brilliant. It was brilliant. It was a good chat. I'd love to do it again. Not that I did.
Bless everyone.
I just listened, and I'm on at 1 p.m. GMT tomorrow. The link for Rumble and YouTube is in there new.
Yay. Jeff?
Yahweh bless everyone.
Amen.
Cool.
And Janusz.
Janusz.
Janusz, I keep on saying Janusz.
Okay. Janusz is a bad entity, yeah. Anyway, no problem at all with it. Get them with kindness, with kindness. That's why we are different, than the Globers. And when they see the opposition, two ways, two sides, of the same coin, we are exactly on opposite coins, the sides of the coin. They will see, okay, there's something not right on this side, and kindness really might attract them, and they'll start looking into it. What's the truth, and it might convince them. Let's hope so.
Amen.
Amen.
No, I agree.
Same thing. Amen. I agree.
So yeah, guys, I just want to say thank you all for coming. I appreciate you. I hope to see you guys all tomorrow. Many, many blessings, and may the pressure be with you. Bye-bye.
Ta-ta.
Ta-ta.
Night, everyone.
Crafted signs of the divine. I'm made for something true. In God's plan, my path renews. Flat earth made by Him, my journey long yet thin. Purpose found in every day, guided by His gentle sway.